Welcome. This question says, using the method of Gauss's law that was shown in class, determine the electric field 2 meters from an infinitely long string of positive charge that has a linear charge density of 6 coulombs per meter. So let's begin by visualizing, and I'm going to visualize my string, my line of positive charge. So if you like, I can put a whole bunch of positives in here. I'm going to not put them so much in the, well, I'll just do it. There's no misunderstanding. And the point of interest is going to be over here somewhere. And that's going to be 2 meters away. And as always, I want to draw a Gaussian surface that helps me determine this value of E. And the symmetries I look for a situation where E is constant on the Gaussian surface, and then I want a situation where either E is parallel to the little area vector, the dA for the window I'm interested in, or E is perpendicular to the area vector. And clearly, whereas before I've tended to use spherical symmetries, that's not going to work in this case because I don't have a spherically symmetrical charge. I have a line of charge. And you know, the first time you do it, it's not obvious, but then you look at homework videos and you see, or worked examples, and you see that there's a better way to do it, and that is, in this case, you take a cylindrical Gaussian surface. So I'm imagining a top surface, and then I'm imagining a sleeve, and the sleeve is such that the point of interest sits on the sleeve. And then we have a bottom surface. I'm going to put the bottom surface dotted so that it's like you're looking through a three-dimensional thing. And what I know about the top surface, if I pick a point, is that the electrical field is going to be perpendicular from my little area vector. And what I know about the bottom surface, I'm going to imagine the point there and do dot, 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 and there's my electrical field sticking out. And that electrical field is going to be perpendicular from that area vector. Clearly the electrical fields are going to be radially symmetric, and they're going to be at 90 degrees to the positive charge. So what that says is that E is perpendicular, there's my sign for perpendicular, to dA on top and bottom surface. So what this means is when I put in my Gauss's law, flux is equal to surface integral of E dot dA, which equals Qn over epsilon naught. If E is perpendicular to dA, then the dot product is 0. And so the top and bottom surfaces are not going to be useful. They're not going to contribute to my equation for finding the electric field. They're going to be 0 flux. So that leaves me with the sleeve. Here's the sleeve. Here's my little doorway, the little window in the sleeve, and here's my dA. And I'm familiar with this. dA is parallel. So I can say on the sleeve, E is constant. That means I can take it out of its integral, and E is parallel to dA. And what that means is that when I expand this as E dot dA becomes E times dA times the cosine of theta. By being parallel, the theta is 0, so it becomes simply the magnitude of E times the magnitude of dA. So I can use that to justify this next step, which is that flux is equal to E. I can take E to the front, integral of dA, which equals Qn over epsilon naught. Well, what is the integral of dA? The surface integral of dA is all the little windows on the sleeve, because we're talking about the sleeve now. So this gives me that we get E times the surface area of the sleeve is going to be the circumference multiplied by the height. So let's have 2 pi r times, let's call the height L. Let's mark it on here. So this is L from there to there, and this is R from there to there. So it's the circumference multiplied by the height. Imagine just cutting this sleeve and laying it out flat so it formed a rectangle. And this equals Q inside over epsilon naught. So now I can say, well, E is equal to, that's going to be Qn over 2 pi r L times epsilon naught. And you may recall we've been saying over and over again that Ke is equal to 1 over 4 pi epsilon naught. So that tells us that 2Ke is equal to 1 over 2 pi epsilon naught. You know, 2 on one side, 2 on the other side, 2 over 4 becomes 1 over 2. So that's where that comes from. So I can say, well, E is equal to, it's going to be Q inside over, rather than the 2 pi epsilon naught, I'm going to put down 2Ke. So that goes away. I've got an R and I've got an L left over, so that's R and L. Q inside, I've got to try and get some kind of value for Q inside. And if I think about it, if the linear charge density, if I know the linear charge density and I know the length, then I can figure out how much charge is inside. So this equals 2Ke over RL. And we use the symbol, we use lambda for the linear charge density, so many coulombs per meter, and the length is L. So, well, the L's cancel, so I have 2Ke lambda over R. And that's a very standard form of answer. That's something that you'll find in the textbooks. So then if I want to put numbers in, I know I have 2Ke. I have my lambda, and my lambda is 6. It's 6 coulombs per meter. And my radius, the distance from the charged string to the point of interest, is 2 meters. So that would be 2. So I can say E is equal to, that's going to be 6Ke newtons per coulomb. And there we have it. If I wanted to, I could figure out what Ke is, and I could work it out actually as a numerical value. But often when we're doing a lot of work or we're in tests, we can leave Ke as a constant in there. So it's a different Gaussian surface, but the approach is the same. I tried to pick a Gaussian surface where my E is constant on that surface, and I tried to pick a Gaussian surface where either the E was parallel to dA or E was perpendicular to dA. If E is perpendicular to dA, I can forget about that surface because it's not going to contribute any flux to the system. And so I could discount the top and the bottom surfaces, but that left the sleeve. And so I said, well, my flux is equal to E integral dA for the sleeve, which equals Q in over epsilon naught. And yeah, the area, the surface area of the sleeve, I imagined cutting this open. I imagined taking that and just cutting it and laying it out, whether that dimension was L and this dimension was 2 pi times R. Just uncoiling the sleeve. And so I got 2 pi R times L, that is my surface area. And then I recall that K equals 1 over 4 pi epsilon naught, so 2Ke must be 1 over 2 pi epsilon naught, so I could substitute in and get rid of the 2 pi and the epsilon naught. And then I substitute in for Q inside. It's going to be the linear charge density, which in this case I'm calling lambda. How many coulombs per meter do you have? Multiplied by the length inside your Gaussian surface. So can you see, if I choose a longer length, I have a bigger L on top because there's more charge inside. But I have a bigger L underneath because there's a bigger area. So it self-regulates and the L's cancel out. And then we end up with this standard form. And just stop for a minute with the standard form. It's an inverse relationship as far as the distance from the wire is concerned, rather than the inverse squared relationship you'd get from a point of charge. So that's interesting. And also it's linearly dependent upon the linear charge density. And clearly if I have more charges squished in, I will get a bigger effect. So that makes sense. And so we get our answer. So a different Gaussian surface, a different approach. Once you've seen it, you remember it. But there we have it.